Welcome to Section 6, Lesson 2. In the previous lesson, we introduced linear systems and solved them graphically by plotting both lines and reading off the intersection. Today, we cover the first algebraic solving method, substitution. Substitution gives exact solutions reliably regardless of how messy the numerical values are, and it works for any system including non-linear ones we will encounter later in the course. The core idea is to use one equation to express one variable in terms of the other, then substitute that expression into the second equation to reduce the two-variable system to a one-variable equation that the Section 3 machinery handles directly. Today we lock in the 5-step procedure and walk through two examples illustrating both the basic case and a slightly harder case with parentheses and fractions. First idea on the board. Substitution converts a two-variable system into a one-variable equation by replacing one of the variables with an algebraic expression for the other. The replacement uses one of the two equations to express y in terms of x or x in terms of y, and then plugs that expression into the second equation. After substitution, the second equation contains only one variable and can be solved using the Section 3 inverse operation procedures. The solved value of that one variable then gets back substituted into the expression to recover the value of the other variable. Second idea. The 5-step procedure is step 1. Choose one of the two equations and solve it for one of the two variables to express that variable as a function of the other. Step 2. Substitute the resulting expression into the other equation, replacing every occurrence of the chosen variable. Step 3. Simplify the resulting one-variable equation. Step 4. Solve the one-variable equation for its variable using inverse operations. Step 5. Back. Substitute the value into the original expression to find the other variable. Verify by plugging both values into both original equations. Third idea. The choice of which equation to solve first and which variable to isolate can make the algebra easier or harder. Look for an equation where one variable already has coefficient 1 or -1, because solving for that variable produces a clean expression with no fractions. If neither equation has such a variable, the substitution still works, but produces a more complex expression with fractions, which the algebra has to handle through the rest of the procedure. The choice is craft, not strict procedure. Any choice produces the correct answer, but a smart choice produces it with less work and fewer error opportunities. Substitution converts a two-variable system into a one-variable equation by replacing one variable with an algebraic expression involving the other. The replacement uses one equation to express y in terms of x, then substitutes that expression into the second equation. The resulting one-variable equation is solved using Section 3 inverse operation techniques. Here is the 5-step procedure. Step 1 is solve. Choose one of the two equations and solve it for one of the two variables. Look for an equation where the coefficient of one variable is plus or minus 1 to keep the algebra clean. Step 2 is substitute. Take the expression for the isolated variable and substitute it into the other equation, replacing every occurrence of that variable with the expression. The resulting equation contains only one variable. Step 3 is simplify. Distribute any multiplications across the substituted expression, combine like terms, and clear any fractions if convenient. The simplified equation is in the form of a standard one-variable linear equation. Step 4 is solve. Apply the Section 3 inverse operation procedures to isolate the remaining variable. The result is a specific numerical value for that variable. Step 5 is back substitute. Plug the solved value into the original expression for the isolated variable from step 1 to find the value of the other variable. Both variables now have specific numerical values, and the system is solved. Verify by plugging both values into both original equations to confirm both are satisfied. The verification catches any algebraic slip in steps 1 through 5 and is essential for reliable answers. Here is the first worked example. Solve the system 2x plus y equals 5 paired with x minus y equals 1 using the substitution method. Step 1. Solve one of the two equations for one of the two variables. The first equation has y with coefficient 1, so solving for y is cleanly y equals 5 minus 2x. Use this expression in the next step. The choice is good because the coefficient of y was already plus 1, so the solving step required no division. Step 2. Substitute the expression for y into the other equation. Take the second equation x minus y equals 1 and replace y with 5 minus 2x. The substituted equation reads x minus the quantity 5 minus 2x equals 1. The y has been eliminated and only x remains. Step 3. Simplify. Distribute the negative sign across the parenthesized chunk x minus 5 plus 2x equals 1. Combine like terms e3x minus 5 equals 1. The simplified equation is now in standard 1 variable form ready to solve. Step 4. Solve for x. Add 5 to both sides. 3x equals 6. Divide by 3x equals 2. The first variable is now solved with the value 2. Step 5. Back substitute. Plug x equals 2 into the expression y equals 5 minus 2x. Y equals 5 minus 2 times 2 equals 5 minus 4 equals 1. The second variable y equals 1. Both variables are now solved. Steps verify. Plug x equals 2 and y equals 1 into both original equations. First equation 2 times 2 plus 1 equals 5. Match. Second equation 2 minus 1 equals 1. Match. Both equations satisfied, so the solution is verified. So the solution is x equals 2, y equals 1. The big lesson from this example is the 5-step procedure executed cleanly. Solve, substitute, simplify, solve, back substitute, verify. Each step is mechanical once practiced. Choosing the right equation to solve first matters. Equations with plus or minus 1 coefficients give the cleanest expressions to substitute. The procedure produces exact answers reliably regardless of the specific numerical values, and it generalizes to non-linear systems and 3-variable systems with the same workflow scaled up. Here is the second worked example. Solve the system 3x plus 2y equals 14 paired with x equals 2y minus 4 using the substitution method. The second equation already has x isolated, which gives substitution a head start and makes this example especially clean. Solve for one variable. The second equation already has x isolated as x equals 2y minus 4, so step 1 is essentially free, no algebra required. The expression for x is 2y minus 4. Step 2. Substitute the expression for x into the first equation. Take 3x plus 2y equals 14 and replace x with 2y minus 4. The substituted equation reads 3 times the quantity 2y minus 4 plus 2y equals 14. Steplify. Distribute the 6y minus 12 plus 2y equals 14. Combine like terms 8y minus 12 equals 14. The simplified equation is in standard 1 variable form ready to solve for y. Step 4. Solve for y. Add 12 to both sides. 8y equals 26. Divide by 80y equals 26 over 8, which simplifies to 13 over 4 when you reduce the fraction. The first variable is now solved with the fractional value 13 over 4. Back substitute. Plug y equals 13 over 4 into the expression x equals 2y minus 4. X equals 2 times 13 over 4 minus 4 equals 26 over 4 minus 4 equals 6.5 minus 4 equals 2.5, which is 5 over 2. The second variable x equals 5 over 2. Step 6. Verify plug x equals 5 over 2 and y equals 13 over 4 into both original equations. First equation 3 times 5 halves plus 2 times 13 fourths equals 15 halves plus 13 halves equals 28 halves equals 14. Match. Second equation 5 halves equals 2 times 13 fourths minus 4 equals 13 halves minus 8 halves equals 5 halves. Match. Both equations are satisfied. So the solution is x equals 5 over 2 and y equals 13 over 4. The big lesson from this example is that substitution produces fractional answers cleanly when the system has them. The procedure is the same 5 steps as before. with the algebra carrying fractions through the substitution and simplification steps without any conceptual change. Real-world systems often have non-integer solutions, and substitution handles them reliably, while the graphical method would struggle to read fractional coordinates accurately. The fraction handling is a craft skill that becomes automatic with practice. The underlying method is the same. 3 mistakes that catch every algebra student during their first weeks of substitution work. Each one is fixable with a small explicit habit applied on every problem. First mistake: solving for one variable but forgetting to back substitute and find the other variable. A student executes steps 1 through 4 cleanly, gets x equals 2, and declares that the answer to the system. The correct answer requires both x and y, found by plugging x equals 2 into the original expression for y. The fix is to always remember the system has 2 variables, and the solution requires both values. The back substitution step is mandatory, not optional. Second mistake: substituting the expression back into the equation it came from instead of into the other equation. A student solves the first equation for y as y equals 5 minus 2x, and then substitutes this expression back into the first equation, getting 2x plus the quantity 5 minus 2x equals 5, which simplifies to 5 equals 5, a useless identity. The fix is to always substitute into the OTHER equation, not the one used to derive the expression. The other equation provides the second constraint that pins down the actual value, while the source equation just gives the identity by construction. Third mistake: sign or distribution error after substitution, especially when the substituted expression has a negative coefficient or follows a minus sign in the target equation. A student substituting y equals 5 minus 2x into x minus y writes x minus 5 minus 2x by mistake, missing that the minus sign in front of the substituted expression must distribute across the entire expression. The correct distribution gives x minus 5 plus 2x. The fix is to always wrap the substituted expression in parentheses immediately and distribute the leading sign carefully through every term. Substitution is the workhorse algebraic technique for solving systems across science, engineering, and applied math. Anywhere a multivariable system needs an exact solution, substitution provides one of the 2 reliable algebraic methods. 4 broad sectors below. In physics, when 2 coupled equations describe a system with 2 unknown parameters like initial velocity and acceleration, substitution provides the standard algebraic path to the unknowns. Each equation expresses one constraint, and substituting one equation into the other reduces the problem to a single equation in one variable. The technique scales naturally to 3 or 4 coupled equations through repeated application, exactly the same 5 steps applied iteratively. In computer algebra systems and symbolic computation software, substitution is one of the primary algorithms for solving systems of equations symbolically. Mathematica, Maple, SymPy, and similar tools implement substitution under the hood when asked to solve a system. The algorithmic version is essentially the same as the manual procedure you learned today, just executed by software at scale across systems with many variables and complicated rules. In finance and economics, equilibrium conditions in models with 2 interacting quantities like price and quantity, supply and demand, or 2 competing investment options reduce to systems of equations that substitution can solve cleanly. Microeconomic equilibrium, optimal portfolio allocation in 2 asset models, and many other applied scenarios use substitution as the primary algebraic tool. In calculus, the technique of implicit differentiation involves treating one variable as an implicit function of the other and substituting expressions from a relation to compute derivatives. Although the calculus operations are different from algebraic substitution, the underlying idea of replacing a variable with an equivalent expression is the same, and the algebra substitution skill from today is the literal foundation. 3 things to take with you from this lesson today. Substitution is the workhorse algebraic method for solving systems of equations, and mastering the 5-step procedure now sets up every harder system solving topic in the rest of the algebra course and into the linear algebra material later. First, the 5-step substitution procedure is solve, substitute, simplify, solve, back, substitute. Solve one of the two equations for one of the variables. Substitute the resulting expression into the other equation. Simplify the resulting one-variable equation. Solve for the remaining variable using inverse operations. Back, substitute the value into the original expression to find the other variable. Verify both values in both original equations as a final step. The 5 steps are mechanical once practiced and produce exact answers reliably regardless of the specific numerical values involved. Second, choose the equation and the variable to isolate strategically before starting. Look for an equation where one of the two variables has coefficient plus or minus 1, because solving for that variable produces a clean expression with no fractions. If neither equation has such a coefficient, any choice works but produces a more complex expression. The strategic choice does not affect correctness but dramatically reduces the algebra burden through the rest of the procedure. Third, the back substitution step in step 5 is essential and must not be skipped. The system has two variables and the solution requires both values. Solving for one variable and stopping leaves the answer incomplete. Always plug the solved value back into the original expression to find the other variable, and always verify both values in both original equations as a final check. The verification catches algebraic slips in any of the earlier steps and is the cheapest insurance against silent errors. The verification step also confirms that you actually solved the system rather than just one of its equations, because both equations must be satisfied for the solution to count. Substitution is one of the two main algebraic methods for solving systems, and the other one comes in the very next lesson of this section. Both methods produce the same exact answers. The choice between them is a craft decision based on which method is more efficient for the specific equations at hand. Coming up next, the lesson called Elimination Method, where instead of substituting one expression into another we add or subtract multiples of the equations to cancel one of the two variables. Elimination is often faster than substitution when both variables have integer coefficients greater than 1, and it generalizes beautifully to much larger systems through the matrix methods covered later in linear algebra. Mastering both substitution and elimination together gives you a complete and reliable toolkit for any standard linear system you will encounter for the rest of the algebra course and into the harder math classes that follow it.